Welcome to Rotational Inertia. So there are two halves to this video. The second half of the video is going to be explaining rotational inertia for calculus use physics classes, and the first half is going to be for algebra physics classes. If you are in a calculus physics class, watch part 1 and 2. If you're in an algebra physics class, just watch part 1. Okay, so let's get started with what exactly is rotational inertia. Inertia is how difficult something is to get into motion, how difficult something is to accelerate, okay? Back with linear physics, when we were dealing with just motion in a line, you had Newton's second law. That means force equals mass times acceleration, okay? Means the more mass you have, the harder you are to accelerate, okay? So up until this point, inertia was just mass. Mass was inertia, and they were the same thing, okay? With rotational inertia, we have Newton's second law in rotational form. Torque equals rotational inertia times angular acceleration, okay? Which means the more rotational inertia, I, you have, the harder you are to accelerate rotationally. So the general equation that we have for rotational inertia is that your rotational inertia I equals mr squared, okay? So this equation applies when you have an object that's rotating around an axis. Let me draw you a picture. Let's say this is my axis, this point, and I have a planet orbiting around that point, okay? So this equation applies when the thing that is rotating, in this case the planet, is not inside the axis. If we were analyzing, let's say, the planet rotating around its own axis, that would be a different story. We wouldn't be using this equation. But since the planet is rotating around its axis that isn't inside it, this is the equation that applies, okay? So what this equation tells us is that in order to induce an angular acceleration, that's going to be harder the more mass this object has, and it's going to be harder the further the object is from your axis of rotation. Great example of that, say this is my water bottle, okay? And the mass here at my water bottle is going to rotate around my wrist joint. It's going to rotate like that. See how fast I can move it? See how easy that is to accelerate? Now, same mass, same water bottle, I'm going to rotate it around my shoulder joint. Much longer radius, much longer. I'm still moving it, but it's a lot harder to accelerate, okay? Here, I went from 0 degrees to 90 degrees in a quarter of a second. Here, I'm going to go from 0 degrees to 90 degrees in like 1 second, okay? So the same acceleration, the same force took me maybe twice the time because it's harder to accelerate, because the rotational inertia is greater, because the radius is greater. There is one step higher, which is when we're dealing with systems that have more than one participant, okay? Let's say we're looking at the orbit of 2 planets around the same axis of rotation, okay? Then the net rotational inertia of the entire system is going to be the sum of all our mr squareds, okay? I'm going to call this R1 M1, and I'm going to call this M2 R2. So let's give ourselves some numbers here so that we know what we're dealing with. If, let's say, M1 equals 10 kilograms, obviously a planet isn't 10 kilograms, just work with me. M2 is 20 kilograms, R1 is 200 meters, R2 is 150 meters, okay? So let's calculate the rotational inertia of the whole system. Let's calculate I net. So the sum here, I'm summing up all of the participants, all of the planets. So this is going to be M1 R1 squared plus M2 R2 squared. And we're going to do 10 times 200 squared plus 20 times 150 squared. Okay? And if you get out your calculator, you're going to find this is 850,000. Okay, 850,000. So that's a big rotational inertia. It's pretty hard to move that. But let's work through a problem here. Let's say I have this exact system. I just calculated its rotational inertia. Let's say I was asked if I were to put a human 30 meters away from the axis of rotation, what force would he need to apply in order to give me an angular acceleration of 0.5 radians per second squared? Okay, so I'm looking at what force does he need to apply 30 meters from the center in order to get this angular acceleration, alpha. Okay? So we're going to use this equation right here. The torque that he needs to apply is equal to our rotational inertia, 850,000, times the angular acceleration we want to induce, 0.5. So the torque in this case is going to be 425,000 Newton meters. That's the torque we need to apply. And remember that our torque is also radius crossed with force. Okay, we're going to assume that he's applying it at 90 degrees. Radius times force equals 30 meters times force. So I'm going to take 425,000 and I'm going to divide it by 30 meters, which means the force that he needs to apply is about 14,000 newtons. Okay? That is a lot of force, 14 kilonewtons. And that's how you would learn how to solve a rotational inertia problem like this. Okay? So, to my algebra friends, let's say you have a disk, and that disk is rotating around its center. So now my axis of rotation is within my object. Okay? You can't use these equations now because your axis of rotation is inside your object. So what you're going to have to do is, usually the problem gives you the rotational inertia, okay? But what I always recommend is, this is the most common thing you encounter, the disk, the solid disk rotating around its center. I'd recommend that you memorize that the rotational inertia of this equals 1/2 mr squared, where m is the total mass of the disk and r is the total radius of the disk measured from its center, axis of rotation. Okay, once you're given the rotational inertia, you'd be able to do all of this math and solve this out. But one more thing that I want to cover with you guys is called the parallel axis theorem. Okay, what is the parallel axis theorem? It's pretty simple. If I have a object rotating around its center of mass, rotating around an axis at its center, then the rotational inertia of it rotating around something else, let's say I took this ball and instead of rotating around its center, I rotated it around a point right here. Let's call the distance between its center and this point, let's call that big R. And this was little r. By moving the axis of rotation to this new point, I have changed the rotational inertia of my object. The new rotational inertia equals the original rotational inertia plus the mass of my object times big R squared, where again, big R is the distance between my center of rotation, or the center of mass, my original center of the object, and my new axis of rotation. Okay? This is my new rotational inertia. Okay? Now, if you want an equation for how to find the rotational inertia of anything, even when the axis is inside the object, come graduate to the calculus class with me. Algebra people, that's all I can teach you. Have a fantastic day. Leave a like. Calculus people, we're in for a ride. Okay. So leaving off from here, we need an equation to calculate the rotational inertia of any object, okay, when it is rotating around an axis of rotation that is inside the object, okay? Using this equation, we can calculate any rotational inertia if we know the rotational inertia at the object's center, or center of mass, rather. So we need an equation to calculate its rotational inertia around its center of mass. And the equation is the rotational inertia equals the integral of r squared dm, okay? So this is basically exactly what I showed you right here, except now it's in a differential form, okay? Actually, let me put it into a differential form so that it's easier for me to explain to you. I'm going to differentiate both sides, and I'm going to get the differential of rotational inertia equals all r squared times the differential mass, okay? Let me take this disk and let me move it over here, okay? What I'm doing in this equation is I'm summing up all the infinitely small contributions to the rotational inertia, okay? What would an infinitely small contribution look like? It would look like an infinitely small mass some distance away from my center, okay? And that's exactly what I'm doing in these equations. An infinitely small contribution to my rotational inertia is an infinitely small mass multiplied by the distance that that infinitely small mass is from my center of rotation squared, okay? In order to solve this integral, I'm going to need to sum up all of the infinitely small pieces of mass in my disk, okay? And that's what the integral is doing. In order to do that, the problem is always going to have to give you a lambda, or a linear mass density, okay? Your lambda is your dmdr, the derivative of mass with respect to radius, okay? It is very important that you memorize what the lambda means. It's going to give you that your linear mass density, lambda, as a function of r, equals, let's say, 3r, okay? And it's not going to tell you that this is your derivative of mass with respect to radius. I like to do is immediately, I like to say lambda equals 3r equals dm dr, okay? Let's analyze what this means. It means the density of my object at radius equals 0 is 0. It means I have very little mass, or almost zero mass, at the center. And as I go out further, radius equals 2, 3, then I have a lot of mass. I have a higher density further out from the center of rotation, okay? So the reason this is useful is this gives me an expression for my mass differential. This gives me an expression for dm, okay? So what I'm going to do is I'm going to write 3r equals dm dr, and I'm going to multiply both sides by dr. So I'm going to get 3r dr equals dm, my mass differential. Now that I have an expression for dm, I can plug this into my integral and say I equals the integral of r squared times 3r dr, okay? Now I can work with this because my integrand is in variables of r and my differential is in terms of r. So this is going to become the 3 times the integral of r to the third dr, and we know how to evaluate this. This is 3 times r to the fourth over 4, all the way from 0 out to my final radius, okay? Let's say that the disk is of radius 2 meters, whatever. We're going to integrate it from 0 to 2. I'm going to say I equals 3 times 2 to the fourth over 4 minus 0 to the fourth over 4. That goes away. I equals 3/4 times 2 to the fourth is 16. I'm going to divide 16 by 4. That's going to give me 3 times 4 is going to give me 12. My rotational inertia here is 12. Cool. That's how we do it in the calculus class. Again, guys, if you need extra help, go join the Discord server or go to meekextrahelp.com. If you deserve it, click the like button. Otherwise, have a fantastic day and enjoy life.